Chemistry lecture number 88, Le Chatelier's principle. Suppose we have a chemical reaction that is in equilibrium. The amount of reactant and product is constant, and the rate at which each is made is also constant. What would happen if we suddenly increase the amount of product or reactant? What if product or reactant is removed? According to Le Chatelier's principle, if a change is made to a system at equilibrium, the system will react to the change to try to restore the equilibrium. Well, Wikipedia gives a pretty good definition of Le Chatelier's principle. When any system at equilibrium is subjected to a change in concentration, temperature, volume, or pressure, then the system readjusts itself to partially counteract the effect of the applied change and a new equilibrium is established. In other words, whenever a system in equilibrium is disturbed, the system will adjust itself in such a way that the effect of the change will be nullified. To illustrate, suppose we have the following chemical reaction occurring at equilibrium. H2 plus I2 gives 2HI, and then these react to form H2 and I2. Now all three substances, H2, I2, and HI, are in the same container. All three substances collide with each other. Occasionally, H2 and I2 will collide to form HI, and occasionally, two HI molecules collide to form H2 and I2. Now suppose we were to increase the amount of one of the reactants, H2. Basically, we toss more H2 into the container. How does the system react to this change or stress that's been added? So the following diagrams show what happens. So let's see if we can move this. All right, so picture number 1 shows the system at equilibrium. So you have H2 and I2, and they are reacting to form HI. All right, and so it's going back and forth at equilibrium. The amounts of each substance stays constant, and all these substances are colliding into each other, but we're getting this reaction and the reverse reaction. All right, picture number 2 right here. Let's see if we can move this around like that. Shows H2 in red being added to the system. So to our container, we've tossed in some extra hydrogen gas. All right, and then picture number 3, that's this one right here, shows that when H2 is added, it reacts with I2 to produce HI. So these H2s that have been added, well, these guys, they react with the iodine that's already there. And what happens is when they react with the iodine that's there, it produces more HI. The equilibrium is being shifted to produce more HI as a response to the addition of H2. So since more HI is being made by the collision of these, the equilibrium is shifting. All right, it's being shifted to the right here. All right, and then the final picture, picture number 4, this one right here, shows that there are now more HI or more product in the system. So these H's in red was originally the H's that were added as reactant. All right, so when we added hydrogen gas, it reacted to form hydrogen iodide, and as a result, there's more product in the system. So, if reactant is added to a system at equilibrium, more product will be made, or the reaction will shift to the right. So a generalized way of showing it is that we have some chemical reaction, A plus B gives C plus D, and then C plus D reacts to form A and B. If you add more A, or more reactant, the equilibrium will shift to the right, and more product will be made as a result. All right. Now, what would happen if we were to add HI or more product to the system? So in this example, the first example we showed what happened when we added more reactant. It shifted things to the right. What would happen if we were to add C or D to the system, or more product? Okay, well, let's take a look and see what happens. Here we have our chemical reaction. H2 plus I2 gives 2HI. We have our system at equilibrium. That's what picture number 5 shows. And then picture number 6 shows HI in red being added to the system. All right, so this HI, these HIs in red, they're being added. So what happens when we throw in these extra HIs? Well, what happens is picture number 7, that's this one right here. Picture number 7 shows that the addition of HI molecules will cause them to react with each other and produce H2 and I2. So these are the HIs that have been tossed into the system, and what happens is they collide with the other HIs that are already there, and when the HIs collide, they react and they form more H2 and I2. All right? So as a result, since more H2 and I2 is being made, the equilibrium is being shifted to the left. All right? If you go in this direction, more H2 and I2 is being made. The addition of this reacts with the HI that's already there. They react and they form more reactant. The equilibrium shifts this way. All right, and let's see. The equilibrium is being Equilibrium is being used to produce more H2 and I2 as a response to the addition of HI. And picture number 8 shows that there are more reactants in the system. So as a result of adding these HIs, more H2 and I2 ends up being made. All right. So each of these HIs represent HI that was originally added, but now they've reacted and they formed H2 and I2. So more product is being made as a result of HI being added to the system. Hold on. If product is added to the system at equilibrium, more reactant will be made, or the reaction will shift to the left. So if you add product to a system at equilibrium, the equilibrium will shift to the left, and more reactant will be made. All right. Now, what would happen if we were to remove product or reactant from the system? Let's see. Well, pictures 9 through 12 show what happens if we remove HI from the system. So, picture number 9 shows the system at equilibrium. So we have H2 plus I2 making 2HI and 2HI making H2 and I2. And we're going to pay attention to these guys, all right? So these are all in equilibrium. These are producing this, and this is producing that. And then picture number 10 shows the product HI being removed from the system. So now we're going to remove some hydrogen iodide from the system. So what happens when we remove hydrogen iodide from the system? Well, if you look at picture number 11 right here, picture number 11 shows H2 and I2 reacting to form HI to compensate for the loss of hydrogen iodide. And the system is shifting to the right. Okay, so these react to form more product. So more product's being made, the equilibrium is shifting in this direction. All right, and then picture number 12 shows that the HI has been replaced, but there's less hydrogen and there's less iodine. All right, so let's sort of summarize what we found here. If product is removed from the system, the reactants will react to form more product, or the reaction shifts to the right. So if you remove product, the equilibrium will shift in this direction, and more product will be made to compensate for the loss of product. Now, why would the reaction shift to the right if the product is removed? Well, I'll tell you why. Now remember that all the reactants and products are in one container and all of them are colliding with each other. Now if some of the HI is removed, there's going to be fewer collisions between HI and H2. All right. H2 is thus more likely to collide with other molecules such as I2. And if there are more collisions between hydrogen and iodine, you're going to get more product, HI being made. All right, so the gist of it is that these are all colliding into each other. If you remove some of the product, then these things are less likely to collide with the product that's already there, and they're more likely to collide with each other. All right, so the reactants are more likely to react with other reactants if you remove product. And since reactants are colliding more with each other, you're going to end up with more product, or product being made. Okay? If a reactant is removed from the system, the products will react to form a reactant, or the reactant will shift to the left. So if I were to remove a reactant from the system, these guys will react and produce more reactant to compensate for the loss of reactant, and the equilibrium will shift to the left. An endothermic reaction at equilibrium can be represented as A plus B plus energy gives C plus D. Remember that an endothermic reaction absorbs energy. Energy is added to the reactants. If we add energy to an endothermic reaction, the equilibrium will shift to the right. So if you add energy, it's almost like adding A or adding B. It'll cause the equilibrium to shift in this direction, and more product is going to be made. If energy is removed from an endothermic reaction, the equilibrium will shift to the left. So if I were to remove this, that's the equivalent of removing A or B. It'll cause the equilibrium to shift in this direction. These will react to compensate for the loss of these things. So in a sense, to compensate for the loss of energy, these will react, and the equilibrium will shift this way, and we'll get more A and more B and more energy. An exothermic reaction at equilibrium can be represented as A plus B gives C plus D plus energy. Remember that energy is produced in an exothermic reaction. Energy can be considered as a product of the reaction. If energy is added to an exothermic reaction, the equilibrium will shift to the left. So, add energy, it's the same as adding more product. It'll cause the equilibrium to shift in this direction, and more A and B is going to be made. If energy is removed from an exothermic reaction, the equilibrium will shift to the right. So if you remove energy, it's the same as removing C or D. Then A and B react to compensate for the loss of product. We can think of energy as a product. The equilibrium will shift in this direction, and more C and D will be made, and more energy will be made also. Pressure affects the equilibrium if the reactants and products are in the gaseous state. When the pressure is increased, the reaction will shift in the direction of the fewest molecules. For example, nitrogen gas, N2, and hydrogen gas, H2, can produce gaseous ammonia. Now suppose we have N2, H2, and NH3 molecules in a container, and the above reaction is occurring at equilibrium. We then increase the pressure on these substances by reducing the volume of the container. Which way will the equilibrium shift? All right, so here's our container, and it contains nitrogen gas, hydrogen gas, and ammonia gas. And then suddenly we squash the container and make it smaller. That's how we increase the pressure. So if we increase the pressure by reducing the volume, which way is this equilibrium going to shift? Is it going to shift in this direction and produce more NH3, or is it going to shift in this direction and produce more N2 and H2? Well, the way you figure it out is on the left-hand side right here, there's one nitrogen molecule and 3 H2 molecules. And that gives us a total of 1 plus 3, 4 molecules on this side. And on the right side, there are 2 NH3, so there are 2 molecules on this side. So 2 molecules on this side, 4 molecules on this side. If you increase the pressure, the equilibrium is going to shift to the right, to the fewest number of molecules. So, summarize, at higher pressure, equilibrium shifts in this way. The equilibrium will shift to the right because there are fewer molecules on the right side. 2 here, 4 here. NH3 is an important substance since it's used to make nitrogen fertilizer. The Haber process is a method of increasing the yield of NH3 in the equilibrium reaction. In 1909, Fritz Haber increased the yield of NH3 by increasing the pressure on the equilibrium reaction. And he also removed some of the heat as it was generated in the reaction. Haber also added a catalyst to the reaction to loosen the strong triple bond between the nitrogen atoms in N2. Nitrogen gas is very unreactive, but adding a catalyst allowed the reaction to reach equilibrium more quickly. Red cabbage juice can be used to demonstrate shifts in equilibrium. Red cabbage contains a pigment called anthocyanin that changes color in the presence of H+ or OH negative. And below is a very simplified chemical equation showing how the color of anthocyanin, which we'll represent with the letter R, changes as it combines with H+ and OH. So if you add OH to the system, the equilibrium will shift to the right and the solution will turn from a red-purple color to a blue-green color. And one way to increase the amount of OH is to add ammonia to the system, which I'm going to demonstrate in a bit. And then if you add H+ to the system, the equilibrium will shift to the left and the solution will turn from a blue-green color to a red-purple color. One way to increase the amount of H+ is to add vinegar to the system. So I have some red cabbage juice. Hold on a second. Right here. Okay, so that's a nice blue color. So the blue color indicates that there's probably more ROH in the system than there is RH. And then what I'm going to do is I'm going to add some H+, some vinegar, and that's going to shift the equilibrium in this way, and it's going to change color. All right. So, all right, so I'm adding H+ to shift the equilibrium to the left. And there we go. All right. All right, so we added H+, the equilibrium shifted in this direction, and we had a sort of a redder color. Now I can shift the equilibrium back in this direction if I add OH. And one way to increase the amount of OH is to add ammonia. So let me get some ammonia. Oops. Okay. And I'm increasing the amount of, here we go. Pretty neat, huh? So when I increased the amount of OH, the equilibrium shifted back to a blue-green color. And I can shift it back again by just adding more H+. And I can just keep doing this ad nauseum. So if I add some more of this stuff, see, I shifted the equilibrium back again. All right, and I can just keep doing this back and forth, but my bowl is starting to get kind of filled up. All right. For a PDF transcript of this lecture, go to www.richardlouis.com. This has been chemistry lecture number 88, Les Chatelier's principle.